So this is the, okay, we'll talk about edge detection. It's something like not very complicated, but it's kind of essential. So let's start with like a little bit kind of like recap or maybe exercise for you guys. So we talk about quite a few filters and so on. Maybe can you fill in the blank like for this, like was D convolved with B? What do you think it's supposed to be? Which one does it look like? So B, of course, is a filter, right? So I would say again, like you can see it's kind of like a high pass and low pass filters. Like which side is high pass, which side is low pass? Vertically high pass or low pass? Oh, someone is. Oh, okay, no, just. So. High pass or low pass vertically? So it's a yes or no question. It's like so I can just maybe high pass, raise your hand or something. Low pass, raise your hand. Everyone fall asleep. Not that way. So I guess it's just first 5 minutes. I'm assuming you guys still awake. But so which okay? Did I explain myself clearly? Like. This is apparently a filter, right? So vertically high pass or low pass, you think is a yes?
Could you like really explicitly explain like when you're doing filtering on images, like what are exactly the low frequencies and high frequencies?
Oh, okay, maybe you missed that part. Let me, I guess I mentioned that, but you guys need to be very careful. The frequency, again, is spatial frequency. It's not light frequency. When we talk about vision, all this stuff, we have light, right? Don't ever mess up with that. It's not frequency about like blue, red, or so on. It's actually the signal frequency, spatial frequency. So therefore, like you expect something low pass. For example, if the signal is low pass, it means that spatially it's not changing that much. So therefore, you expect the image is kind of smooth. So something like for example, this one I would say like have probably the high pass component is not missing because like the whole image is kind of smooth. So high pass will be like just the opposite. The smooth component will be gone. So if you think of the what will be the smooth component will be say the FH image, right? So therefore, like this one, I can. Oh, okay, this one is not a good example, but if you, yeah, it's a good example if you consider grade column, grade scale, meaning that it's like 0. I mean, basically, if you remove the FH of the image will be just have edges. Actually, the edge image is kind of like only remaining the high pass component. So then again, like what do you think? Like this one would be, like vertically is high pass or low pass? Oh, and of course, like, if you look at this, like in terms of values, this thing, the dark value, meaning is low. Let's say it's a small value, and then bright value is a big value. So maybe I translate this into numbers. Maybe let's say I just roughly say that. Like let's say it's like from 0 to 1, maybe something value like okay. This is why they don't have Control C. It's always like so stupid. So I need to be very careful when I write. Let's say have value. That's I just use here. is kind of look like this way, more or less, I see. Actually, I used to create a number that I can actually decompose. This way I cannot decompose, I see. Maybe actually this one really cannot be decomposed if I look at it now. So, but let's see if I can just really try to decompose it. Along this will be kind of yeah, I'm not sure actually. Now, honestly, now more I look into it, I'm not so sure. Like, I can actually decompose this. Actually, maybe I shouldn't. Oh, okay, I see the problem now. I shouldn't interpret like here as 0. That doesn't make sense. Probably this here it should be 0, and this is a minus value. Oh, then it makes sense. So 0 is here. So this will be, let's say, minus 2, something like, and then maybe I have minus 1 here, 1, 1. Ah, okay, now it makes sense, right? Something like that. Do you agree with me? So this, like, they shifted the scale basically. So the really small number, really negative number is like all dark here. The really positive number is like white here. So then in that case, in this sense, it's pretty messy. I generated another line. In this sense, this I can actually decompose into like 1, 0, minus 1 multiplied by 1, 2, 1, right? Sorry, like, can you see that? Like, so then like you can see that actually vertically it's kind of high pass, but horizontally it's a low pass. So now if I give you this information, actually this is actually the only image it makes sense here is just this one, right? Because so vertically high pass meaning that like you detect the horizontal edges, and the horizontal low pass just move it a little bit, kind of like you smooth the image a little bit horizontally, and then generate the find the horizontal edges. So how about the second one? Maybe I should clean this thing a little bit. Yeah. A is coming from so you're trying to again like convolve these two things, I will get you A, okay? So yes, you got that. Like C and B you will get you will basically get A. And then how about C? Like F is from D convolve with actually F this just looks like D and actually D and E. Actually, E would be just a horizontal shift, right? If you look at it, it's just horizontal shift. Therefore, you see a tiny shift here. Like maybe it's not clear from you, but there's a Let's see the shift of the image. So this DME, and we just have DMB and G, right? And then DMD is basically just a mask. It's basically here. It's generated image I there. So this is I, let's say. So just another kind of exercise for you for looking at filter and convolution. And again, even though I say convolution, but correlation will be kind of the same for most of these cases here, because remember, correlation, the only difference is that you do a flip before you do the, convolution is basically you do a flip of one of the filter before you do the correlation. So in several of these cases, basically filter is symmetric, so therefore there will be no difference. So now we are going to talk about, actually I mentioned to you last time, actually some of you guys asked about, but she's not here, I forgot her name, about whether you can just upsample the image to get more information or so on. That's something that I did many years ago. Let's see. I need to change to something else again to click this. Shut down the music. Wow. I cannot shut down the music. But anyway. It's a bit distracting. So this is a tiny demo about supersolution. So let's see. Let me go back a little bit. Basically, here, I have a bunch of images. It's not just one. I have more than one. That's what I meant. If you have one, it's a little bit kind of hopeless, I would say. You can do some enhancement to the image, but typically you won't get more information. Or sometimes you use face recognition. Because for human face, you have some kind of prior statistics, you know what humans are supposed to look like. So therefore, you can artificially create some information there to make it look like more human. Even you look like first the image is really blue, but if you have some actual information, it's hard for you to. For example, here it's a sign there far away. Right? It used to be really not so clear the words supposed to be. But if let me just move forward. I have many images and combine them together. So this is take a long time. So eventually you will be able to just incorporate the information. So, but honestly, for this kind of method, you need to be pretty. Your image need to be pretty well aligned. So in the sense and of course if all the images are the same, then there will be no actual new information, right? So you need to have multiple images shooting the same thing, but each of them provide you a little bit different information. Then in that case, actually, if your hands shake a little bit, it helps. So how I generate the image is I put the camera there and I just and then then there's a little bit shaking, so therefore I have sequence of images that capture a little bit different kind of have some tiny differences, a tiny displacement. So I won't talk about this today. Maybe if I have time, maybe in the future, then I will talk about that. But honestly, I forgot what I did then, so I need to take it up. So as I said, I will just talk about edge detection. So there's some slide for edges. Of course, all of you guys know what an edge is. It's very kind of obvious to everyone. And a very famous experiment by some biologists like Hubble and Wiesel, I guess, in 60s is they actually they try to pop into the neuron of a cat's brain, and they did want to see like what kind of stimuli can like activate the neuron. So they tried lots of different patterns, and they almost gave up. And eventually, they just I guess by mistake they came across like just a line that they are not intentionally put that, and then like when they adjust the line and they find that the neurons just fire. So then they, for example, here as you can see, like when the cat see a vertical line, then the neuron just fire like crazily. Then they realized that like even for our brain, like they do have some low level kind of vision processing, basically doing this kind of edge detection. So and for us, like it's pretty amazing if you think of that. We can just look from a little bit sketch, and we can kind of visualize and understand what is that picture is. Even though like you look at this here, there's lots of missing information, but I don't know since when, maybe since we are 5 years old, I don't know since when we have this capability, but that's definitely was trained. It's not something that we were born with, like when we were like 1-2 years old. So most likely, I don't know. That's you can ask your mom when you kind of like begins to realize sketches. I mean, understand sketches, and I guess like that's another experiment like by some fellows. Like they try to see the brain activation like by both like images and kind of edges of the images. So they just want to argue that like even just with the lines alone, they still have like quite a bit of activations compared with like just the entire photograph. So and there's some other works. Okay, let me go to this one. It's kind of interesting. It's some work by Elder in 1999. So what he argues is that like really just from the edge image you can get lots of information. So what he did is like he started with a kind of just a photo like this, and then he extract the edges, and he tried to re-synthesize the entire image. And this is like how after he do a couple of processing that he end up with this image. So then he argues that really we can have lots of information from the edges. So let's see. Of course, there are lots of use for edge detection, not just not just for interest of the biologists, and in terms of computer vision, we can use that to recognize objects somehow, maybe, I don't know, probably not the easiest way to recognize object. And at least we can do lots of geometry, like because for example, if we may talk about next week. For example, if you want to kind of model your 3D viewpoint of your scene, then it's better to extract the edges and kind of like find out the geometry of the object. Like for example, you want to look at where's the vanishing point and so on and so forth. If you can find all the edges, it will be much easier to construct that 3D model. So of course edges has many types, like but we won't distinguish that much, but we just want to let you aware of that. Like you can have edges because of kind of the depth discontinuity of the actual scene there, or so that no, that is not depth discontinuity. This is a surface normal discontinuity, and that's a depth discontinuity. You can have like just different colors, and so on and so forth. So edge detection has been kind of like studied for many years. So those earliest one will be just as what we look at the beginning. Like we can use, like, for example, high-pass filter. And if you think of high-pass filter, the simplest high-pass filter will be simply the derivative of the image, kind of, because if you take the difference of the image, you can think of that filter like, let's see. So you can think of like filter like -1, this kind of filter. It's a high pass. This is called high filter actually. It's high. is some kind of high-pass filter also. And of course, this will be just an approximation of a derivative, right? So if I put a 1/2 here, let's say, it'll be just a kind of approximation of derivative in one direction. So as I mentioned, there are many ways to approximate this derivative in practice when we have discrete signal here, because our image, after all, will be like discrete, right? Pixel-wise, it's not continuous. So we can either do a forward approximation, let's say we use the next pixel subtract I should say, like, we will have the current pixel subtract the last pixel, or we can have a forward approximation, like have the next pixel subtract the current pixel. Actually, it doesn't make sense, this equation. Yeah, and also like you can have, say, do a central approximation, like the next pixel count minus the previous pixel. And this is quite simple. So correspondingly, you will have filter like this, right? So simply have filter like this. So we just have a 1D example. Okay, let's see. Okay. If I have 2D, it will be like this, right? We will do kind of horizontally. We have high-pass filter horizontally. Also vertically have another high-pass filter. So then afterward, we can merge them together. So I mean, like one of them, you kind of like trying to detect. So let's try to quiz you again. Like this is going to detect what? Horizontal or vertical edges?
Vertical edges.
Yes, still this will detect like vertical edges, right? This will detect horizontal edges. And so give a concrete example here. Let's say if I have a filter like this, so then like if you go for that, so what do I get like from this image? Of course, this is a very small image, only 5 by 5. If I apply the filter on this image, or like this patch,
it won't detect the vertical edge.
Yes. And the result will be just all zeros, right? So if you do a convolution of this to this guy here, or like a correlation to this guy here, then basically all zeros, right? So because basically, for example, if I compute this value at this place here, then we will try to do a dot product of this patch with this guy, right? So then I will have like 10 plus 10 plus 20 plus 0 plus 0 plus 0 minus 10 minus 10 minus 20. I will get 0. So I'm so far for all the other locations. And how about this one? If I use this filter, like what do I get?
We will get some value at the transition between 10 to 20.
Yes, we will have some values here. Kind of like, for example, if you look at the values here, so again, you compute the values here, it will be like do a dot product of this patch with this patch, right? So I have minus 10, minus 10, minus 10, minus 10, minus 10, plus 20, plus 20, plus 20. So I have 30 there, something like, or I have 1/1, so I have 10 there. So I have 10, 10, 10 here, something like that. So you may have some other values here, depends on how you handle the boundary. But anyway, here you got a bunch of 10s. So now, so as you can see, it's very easy to detect edges this way. But the problem is that like the problem is really let me go. But before I look into one of these problem, let's look at like how we detect like not horizontal and vertical edges. So what we can do is like we will look into the gradient in both directions, right? So if your edges doesn't end up to be like horizontal or vertical, it's like, again, I cannot erase what I just written. If it's like some diagonal, then basically if you have this horizontal or vertical gradient filter, you kind of detect it a bit, but will have smaller magnitude, right? Your filter result will be not as big as like when it's horizontal or vertically. And then like if you combine, if you look at the result from both filters, so you can basically essentially get the gradient of that, right? So when you apply the horizontal filter, so what you can think of, you're kind of computing just the horizontal values of the gradient, and if you use the vertical filter, you're computing just the y component of the gradient values. So if you combine these together, you have the anti-gradient. So with the anti-gradient, you can say get the magnitude of your or the strain of the edge as basically just the strain of the gradient, right? So you just compute the strain of the gradients will be the edge strain. At the same time, the direction will be just the direction of your gradient, right? Or, I should be careful. The direction will be the tangent of your gradient, right? Because it's actually pointing to the tangent of the edge. So for example, you have an edge here, so your gradient should be like in this direction, right? So you're changing in this direction, so your gradient will be perpendicular to your edge, something like that. So any question here? So with that, like we can not only detect like horizontal and vertical edges, but we can also like detect like kind of diagonal edges of any angles. So this is an example. Again, like which one is the horizontal filter, which one is vertical filter? Now can you spot that? Like this one on the left is horizontal filter or vertical filter? It's computing a horizontal gradient or the vertical gradient. Again? Yes. That one should be horizontal. That's the x direction. This one will be the vertical. So this is like you have all these vertical edges is getting from the horizontal filter, and then the horizontal gradient, or the gradient in the horizontal direction. Yeah, or the derivative over the x direction, more precisely. So this. So the problem now we can talk about like the problems of like what we just explained, this simple edge filter. The problem is that like typically your image is like kind of noisier. So if you just compute the derivative from scratch, you can catch lots of noises. So like this one, you here you get you have the strong edges here, but you can be kind of like what's that word for that? Like kind of over. What's that word for that? Can anyone help me with English? Like you're kind of flooded? No, it's like water cover you. Like what's that word for that? Water covering you.
Over
Something. There's water like overshadow. No, not that word. Like overflow seems like okay or saturated. No, overflow seems like okay. Is that overflow? I don't know. I don't know. Maybe I created a word and thought it's a real word. Anyway, so but you understand my meaning, right? So the noise will be too strong that it's just you will have, like, for example, here we give an example. So this is water noisy signal. So if I just simply take the gradient here, or I take the derivative here, you cannot find this edge here because you just kind of covered by all these noises here. Drowned. I'm looking for drowned by all the noises there. So for example, this is an actual image of Einstein, and if the original image is a little bit noisy, so again, oh, I don't have an example, but anyway, so of course, like we know a solution for that. A solution will be simply first try to remove the noise if we can. So we can, let's say, do some simple filtering that we kind of study in the several past classes. So for example, we can do some mean filter, Gaussian filters, median filters, and so on. So the simplest one will be we can, let's say, use a Gaussian filter. Like we have a Gaussian filter going through that, and then we have a smoothened signal a little bit. Then I just take the derivative. Then I will find the edge here. And one thing, like, so basically we have operation like this, right? What we want is like first convolve with some low pass filter, let's say Gaussian filter, and then take the derivative. So, and convolution is like this, right? So basically if I have convolution, this basically either integral or summation, that with this is the image, this is the filter. So if I take the derivative of these guys, note that I take a derivative with respect to x here, right? So, but this integral is with respect to this dummy variable x pi here. So then this derivative go all the way inside, take the derivative of g here, right? So therefore it's equal to this guy. So therefore this operation can be changed into this one. So that means that like I don't actually need to do it two steps. First, smoothen that and take the derivative. I can just consider that as one filter. So it's basically have a filter that kind of like taking the derivative of this Gaussian filter here. So and derivative of this Gaussian filter looks like this. And then I will just directly apply this filter to in this image, or directly convolve this to this guy here. And in two-dimensional, what you get is like something like this. The derivative you have this kind of funny shape here, and we'll just apply this like in the x direction and then in the y direction, and as just like what we what we studied earlier. Afterward, we have like one component correspond to the gradient in the horizontal direction, and the other correspond to the gradient in the vertical direction. Then we can combine these two components to get the edge strength, also the direction of the edge. And this is known as the derivative of Gaussian filter. And if you apply that to this image, more or less you get this. And I like to mention that one very simple filter is very similar to Sobel filter. So it's basically it's again like it's a smoothen, but the exact filter is just like that, right? If I apply the gradient just horizontally without any smoothing, then I will have this pure edge filter that if I only consider the filter patch with size like 3 by 3, this have just of course I can decompose that into this one here. Oh, actually I still have a little bit smoothing, right? This is a little bit layer smoothing, but I don't smooth in the both horizontal and vertical direction. I only smooth in the when I do apply the filter horizontally, I only smooth in the vertical direction. So I smooth in the vertical direction and then kind of taking derivative in the horizontal direction. And I can have a different smoothing that is a little bit more like a Gaussian, that's called a Sobel filter. And just like to mention it because it's kind of famous also. Besides the Canny edge detector that we mentioned later on. And therefore, like, so this is just elaboration of last slide. So we have like, this is the horizontal component of the Sobel filter, and this will be the vertical component. erase my. Oh, this is gone now. So of course, after we get both components, again, like every time it's the same thing. Then you have the x component, y component. You can find the edge strength, and then you can find the angle of the edges. So some example here that is doing reasonably good job, like for this image, vertical component, horizontal component, and then combine together, just show the edge strength here. So there's some problem for Sobel filter, but actually in general for like some of these more simple edge detector is always like they have, let me go to exactly, they don't always have kind of like so-called robustness to noise. For example, this is the ground truth, but due to noise you may detect edges like that you may miss some pixel and got disconnected the edges, or you don't have a very good localization in the sense that you want to get as close as the ground truth as possible. And there's some issue also, like there will be too many responses. Like you want to detect one edge, but your edge just become very fake. So one of the very famous attempts to solve the issues I just mentioned is the Canny edge detector that still quite a bit used nowadays. Actually, if you go to OpenCV library or like your MATLAB, you can easily pull out the Canny edge detector. And I'll just kind of quickly go through the kind of the basic of Canny edge detector. And by the way, this is also a really well cited paper, like more than 10,000 citations, actually 20,000 citations. So first of all, like the first step would be like we want to convert if you have a color image, first convert into a grayscale image, and then afterward, you just use the derivative Gaussian filter that we mentioned earlier. So we get the x component and y component. So it's basically the same as like what we discussed earlier. So then afterward, then we have the magnitude and the gradient, right? Again, we will find the magnitude of that x and y components, and that will give us the gradient images, just the gradient magnitudes that we had earlier. So now the difference is that like Canny edge detector will impose some additional steps. So basically, first step, it will do something called long maximum suppression. If you remember, like earlier, we have some of this problem that like you may detect an edge, but because you just compute based on the edge strengths, you can have the edges pretty wide. So you have more than one pixels. Like for basically you have edge like that, but eventually you detect something like this is the entire edge. That's not really quite desirable. So what they do is pretty simple. Basically, they were just trying to suppress everything that it doesn't look like to be a maximum. So basically, if you have several of these, maybe like several of these pixels is considered as edges, then it will try to look into each of them to see if they are really maximum. So for them to be maximum, they will just look into the gradient direction. Let's say the gradient direction is here. And then for this pixel here, it will look into like the adjacent pixels and to see if the adjacent pixel is smaller than itself. So it's more like this, right? If you are here, then you, let's say the gradient is in this direction, then you look into these two. Of course, these two pixel value, you don't have that, but you can interpolate that, right? You can interpolate these two to get this one, interpolate these two to get this one, and then try to see if like these two guys are actually whether they are smaller than this one Q here. If it's smaller, then it's okay. Then we will keep the pixel there, saying that okay, this is really a pixel for the edge. If it's not, then we just discard that. And this is like before kind of suppression. You can see like this is pretty wide, the edge, detector edge. So after the suppression, the kind of the edge got like much thinner. So, and they have also one additional step. So one additional step they call like Hysteresis thresholding, and it's kind of like an adaptive thresholding. Basically, they will set two values, like a high threshold and low threshold. So basically, if it's bigger than the high threshold, we'll just say, okay, this is definitely an edge. So we'll keep that. So if like lower than the low threshold, we'll just definitely saying that it's a noise. So we'll just discard that. So what is those pixels in between, we'll say is like weak edges. So what they do is like they will start with the strong edge and try to kind of interpolate across the weak edge and trying to extend those weak edge, and then make a connected component. And if you're interested, you can look into the Siliski textbook, but yeah, I didn't look into that, so I cannot explain anything to you. So right now, at least. So this is result for Canny detector, edge detector. It's decent. So as you can see, we have image like this. It kind of extracted most of the edges here. Of course, you need to tune this threshold like a little bit, like that we mentioned earlier, the high threshold and the low threshold. And also this will be affected by the Gaussian filter also, because the first step, remember, is we have a derivative of Gaussian filter, right? So if you change the width of the Gaussian filter or like the spread of the Gaussian filter, you will get different results as well. So basically, if it's smaller, the Gaussian filter, then you will get basically more edges, or like you expect to have finer detail. If you have a kind of wider Gaussian filter, you will kind of smoothen out more edges, so you get less. Smoothen out more the image, then you have less edges left behind. So and that's basically it for the Canny edge detector. And for MATLAB, you can just put it out as a function called edge. And the final slide here, I just want to show you this. This is pulled out from a Palmy paper, like just 2011. Probably not the latest one. I didn't check whether they had later paper like in this area, but as you can see, we're still quite far away from human. I don't know why it just keep doing that. It's still quite far away from human. Wow, this getting goes. I guess I will just remove. And if you look at that here, where's Canny detector? Let's see, it's hard for you to see maybe. Canny detector is here. So it's not the state of the art anymore. There's some better edge detector. If you're interested, actually, you can think of this as a project as well, to look into some of this edge detector and see if you can even improve your edge detector. Actually, one project maybe, like I just give a throwaway like kind of ideas. Let's say you can, for example, like look into one of these edge detector and try to implement that. Of course, if you're going to do project like this, it's not sufficient. Go into OpenCV and pull out the function and then, okay, I want this on several images and that's it. That won't be a good project. Or like it won't be reasonable. Let's say you pull out like 10 different functions of this edge detector, and then you say you compare like this 10 edge detector for this a bunch of images. And so I rather like you look into any particular edge detector you're interested in and really try to re-implement that. And maybe in the process you find out, okay, this maybe I do this rather than this, then actually I will get a little bit better result, something like that. That would be a reasonably good project as well. So, and that's all for me, at least for the slides. Let's see. And for the rest of the time, maybe I will continue to spend a little bit time about, like, let's say some OpenCV and Python and stuff like that. So last time I talked about like doing some Linux stuff. Oh, okay, maybe I can make it bigger. Oh, by the way, this thing, who knows what is this? Actually, I'm showing this. I don't know. Who knows what is this? I mean, like this interface stuff like that. I have the name here though, like if you are aware of that. Do you know what's this? I mean, like what I mean is like the interface here, like this one. Huh?
I don't know what you mean.
Yeah, I'm sorry. Like, let me just put it in a better way. Maybe I should show you like a little bit. Like this thing, I can write Python code here. It's like an IDE, but if you will play with Mathematica before, you know, Mathematica has something a little bit similar that they call it kind of a notebook that you can write some node there, you can write some code there. Then you can press, for example, Shift-Enter, you run that part of the code.
REPL?
Huh?
Like a recursive programming environment thing?
Kind of. Actually, this started as like something called IPython. Then they changed the name called Jupyter now. Mm-hmm. And the nice thing here is like it's good for, I guess, teaching purposes or like for presentation maybe. Because like you can put codes and nodes at the same places, and you can actually this is my new computer. I didn't put in lots of kernels here, but actually you can find kernels for this thing. For example, basically all the languages you can run like this. You just like insert different kernels. For example, I have Optiv here. Basically, you can insert MATLAB here also. Of course, MATLAB has a quite nice IDE. I don't really need that, and maybe Ruby, or like maybe they have this something similar to MATLAB. I forgot the name. So anyway, like so, but this is Jupyter, and we talked about a little bit Linux last time. So assuming you guys really going to install Linux and trying to play with that, one thing I would suggest you to first set up a virtual environment. So I will assume most of you, like if you use Linux, will also use Python because it's easier at least. So and it's popular. So you can set up a virtual environment. So because of course, for example, if your distribution like Ubuntu, they have the system Python there. You don't want to install lots of your libraries there, or then maybe you update the libraries there directly. Maybe it will screw up other things. I have some conflicting things. So the virtual environment will be like this. You can say have an ATP install or ATP get install, like called Python virtual environment. Then you can just run like this. Then we'll create a virtual environment, let's say called P2 in this case, that with Python 2. If we want to run Python 3 instead, you can also specify what kind of Python version. Say I can say it's using Python 3 here. So then afterward, when I use it, I can just source this P2 that's already created, like being activated. Let's see if I have a terminal here. Let me just open a terminal maybe. So I already created a virtual environment. Actually, I showed you last time I did that, but maybe you did not aware of that. So I have this virtual environment. It's called P2. When I source activate that, like if I install anything here with pip install, then everything won't be installed into the system Python environment, but instead I install into this virtual environment. So and then like if you guys going to use OpenCV, it's really simple. I mean, unless you are going to use some, actually several years back when I do a company project, we use some particular kind of libraries and functions that we need to compile from scratch. But I guess most of the time, like for you guys, you can just simply install from the package manager, the PIP package manager. So then you can just install like PIP install, so it's extremely simple. So of course I already installed that here. So if I want PIP install here, it will say already installed that. Oh, yeah, actually here it's also complaining my PIP is kind of not upgrade, not the latest version. I may upgrade that. What? PIP install upgrade PIP. So I upgraded to the latest version. Oh, by the way, if you you can specify what version you want to use. For example, like my OpenCV here, like -OpenCV, I can, let's say if I don't want the version that specified by the OS, I can specify the version, let's say. You can, for example, if I PIP install that OpenCV, maybe I put like this, maybe like this. Yeah, it will show you what kind of versions is available here. So 4.00 is available, for example, like 3.45 or so and so forth. And as I mentioned, you can have /u to upgrade that to the latest version. And one thing is that ATP, like PIP has a search function, so I can PIP search, for example, like OpenCV. It will search like related packages in the. So just a bunch of that. Like you can look into that, like lots of stuff. So let's give an example. Like here, I'm using the environment here. The kernel is exactly the. Oops. Let's see. The kernel is exactly the kernel that. Yeah, basically, actually, I want the Jupyter under this virtual environment, so therefore it's already using this kernel here. So let's say if I just write some code here, so you see like I use CV2, the library CV2, and also matplotlib. Matplotlib is like a kind of matplotlib function library. It's kind of similar to the matplotlib function. So it's like, and again, like if you import anything, you can find it. It doesn't want, just PIP search that library. Probably you can find that, and then you just install that. So I run that, and also I have a linear image in my folder, and I can use the I don't know why it doesn't show anyway. Image cannot convert to float. Did I read that? No, actually I'm not. Oh, wait a sec. Or maybe this folder actually does not have that image. Where did I start that? I forgot. Let's see. Yeah, I think I moved the. Yeah. Where did I put that? Okay, I found it. So let's try again. So I should have the image in this folder now. So yeah, this is here. So as you can see, if I run this, is showing this here. So now it should show the image. And I need to use this magic thing to just say it's going to show inline or something, whatever. So, and you can see like the color is a bit off, right? As I mentioned last time, the color is a bit off because OpenCV interpret the color differently from, let's say, MATLAB. And when they read out the image, or I should say the matplotlib interpret image differently from OpenCV. So OpenCV open the image that the RGB components does not order the same way as matplotlib. So let's say if I let's resize the image, and also like I rearrange the image component, the color components a little bit. So here I have like a numpy. This is a numpy function. If you see earlier, I kind of import the numpy library, right? The numpy library is something kind of like MATLAB. So you can create matrices and do kind of like quick prototyping, like in doing kind of scientific computations. So here I use a Finite function. It's basically saying that I'm generating a matrix, have the same size of this image here, and then I rearrange the color component as you can see here. So then if I show it now, it's like, okay, now it looks reasonable. Oh, by the way, like, do you guys recognize this image? I saw you nodding.
We use it a lot in image processing.
Yes. Yeah, this is a very famous. Do you know where it came from? I think it came from like some Playboy magazine in, I don't know, like 50s or 60s. I don't know what year is that. Yeah. So anyway, but it's very common in image processing. Like people just so anyway, I don't know whether this lady is still here or like whether she passed away already. So let's say I just extract the web component here. This line here, I extract the web component. I set the web component to be 0. So here I want to like kind of emphasize one thing. This is kind of when you use MATLAB, this kind of you're kind of surprised by the results because as you can see here, I pull out the web component here. Right? If you are playing with MATLAB will be what's that called? Like I am not software engineer, so I don't know how do you say it. So whenever you are assigned to the new variable from the old variables, you make a copy. You basically, so therefore you make changes for the new variables, it won't affect the old variable, right? But in this case here, for some cases, for example, for here, when I pull out that component, actually they are linked. This is just building a kind of a symbolic link of this variable R and also the wet component of that image. So therefore, when I change anything for this R variables, it also directly changed the image. So as you can see, like the image was changed directly. And let's see. You can do some filter. I'll skip the filter things. I can do Canny detectors. And here, maybe I show this one. It's just I can do just a couple lines of code to do a have a video capture. So for MATLAB, I don't think it's so convenient, but for OpenCV, it's quite simple. As you can see, like I can put a video capture module here, and then I'll just capture frame, starting to capture frame, and then I'll have a kind of for loop here, and then I'll break it whenever someone hit escape or hit Q here. So each time I'll just showing the image like on screen, and here I forgot which and which. So I set some property here to make it show full screen. So if it runs properly, yeah, it's see me now. something like. So I shouldn't be on the screen. It's better my bottle on the screen. Okay, anyway. So I can go back outside. Oh, okay. Please go back. Okay, yes. So, and we do some edge detector here, right? Edge detection today. So let's try edge detection. So here I just repeat the same thing, but I change to grayscale here, right? RGB to grayscale. I have an image now, it's in grayscale. And then I have a Canny detector here. So with the low threshold is like 10, high threshold is 100. So we can see like what we're going to get, so something like this. So it's pretty much real time. That's pretty nice. So, and I can play with the threshold a bit. So let's see. Remember what's the low threshold and high threshold again? Like if I increase the low threshold, do you expect more edges or fewer edges? I need to think also, like more or no, I think it's fewer. Actually, the low threshold, everything below the low threshold is considered really garbage. So everything between the low and high threshold is considered as weak edges. So potentially they can still be edges. So maybe I can. I'm not sure you remember what you saw, but let's say if I increase it a bit, yeah, it's a little bit cleaner now. So I kind of like less number of weak edges. So I can. How about high threshold? Do you remember what high threshold means? So if I lower high threshold, do you expect to see more edges or fewer edges? Lower. Lower high threshold will be fewer or more? More. Yeah, more. Because everything above high threshold is considered definitely as edges. So if I lower the high threshold, let's say I lower to, let's say, 60, then I don't know. Yeah, maybe it's still hard to see, I guess. Right? So I don't know what is this. Actually, what they're detecting here. I don't know what. It's weird. I don't know what is this actually. Huh? Light. Anyway. So yeah, but it's fun. I mean, like this is of course it's a new thing for you guys most likely, but comparing to MATLAB, you can easily make something application real time, and actually it's much faster than MATLAB. Potentially, of course, many of these operations you can also use NumPy to do that. For example, NumPy have filterings and so on. But OpenCV supposing is the most optimized library in that aspect. So when you use OpenCV, it'll be like, of course there are other libraries also. What's that name? I forgot. But dlib or something. But you can stick with OpenCV more or less. So OpenCV will be like a couple of times faster than NumPy for many operations. And most likely we were faster than MATLAB also for many of these stuffs. So I guess I will just stop here. So I will talk to you guys next Tuesday.